Alrighty, hello everybody, and welcome back to Civil Engineering. Today we're going to be going through activity 323, which is beam analysis. And so, in terms of a beam, what is it? It is a structural member that carries a load that is applied transverse to its length. It is used in floors and roofs, and it also may be called floor joists, stringers, floor beams, or also girders. So you can see we've got the beam down here. We're going to also have supports on those. So we have two supports in this scenario. And then we also have the live load of these occupants that are on top of this beam. So in terms of beam analysis, beams are designed to carry the shear and bending moment caused by design loads. And so shear and bending moment, also these design loads and the support forces, these are all things that we're going to be looking at in terms of the beam analysis. So we can chase the load. And so the loads are initially applied to the building surface, right? So that's on the floor or the roof. And then what's going to happen is these loads are going to be transferred to beams, which transfer the load to another building component, which most of the time is going to be the girders, right? So in terms of a lot of things, most of things in civil engineering, we always want to be reaching static equilibrium. Now, in your physics class, you ended up learning about this, and so this is a nice little recap. But what static equilibrium is it's the state of an object in which the forces applied counteract each other so that the object remains stationary. A beam must be in static equilibrium to successfully carry loads. As you can imagine, if this beam ends up moving or accelerates, it's not going to be a good thing. So the loads or forces applied to the beam from the roof or floor must be resisted by forces from the beam supports. And so this is where we start to get into Newton's third law, action-reaction. And so we're going to end up having applied load. And what should be the case is that these two reaction forces are going to be equal but opposite to this applied load. So the resisting forces, what we call those are the reaction forces. And so those are in green down here. And forces are often referred to as vectors. Now, vectors are different from a scalar value. A scalar value is just a magnitude, right? And so 55 miles per hour, for instance, would be a scalar value. Now, if I would end up saying 55 miles per hour east, that would be the case where that is a vector because that includes magnitude, which is the speed that I'm traveling, but then also the direction. And so these forces here, if we know the certain magnitude for this force, and we know that it's going down, that is a vector. And it's the same scenario here for these reaction forces as well. So in terms of reaction forces, these can be linear or also rotational. So a linear reaction is often going to be called a shear reaction. And we're going to represent that using F or R. We're going to also have subscripts as well, where if it's at point A, it'll be F subscript A. Or if it's at point B, F subscript 2. Same case for R. Now, a rotational reaction is often called a moment reaction. Now, moment you've definitely heard of before. And so we're going to be reviewing that as well. And it is the same case that we'll calculate the moments about different points. And so say if it's at point A, we'll end up having M subscript A. The reaction forces must balance the applied forces. And so that's where we get to the sum of the forces is equal to 0 or sum of the moment is equal to 0. Before we get to that point, though, here's some of the beam supports, ways that we can end up, or different methods that we can support beams. And this dictates also the types of reaction forces from the supporting members. So if you look at this, you'll see that we've got the roller here. So for a roller, that's going to allow the beam's end to actually move to the left and to the right. And so for that reason, we're only going to have a reaction force that's going to be vertical. So it's only going to be the Y component of the force. If we have a pin connection, there's going to be basically two supporting forces. That's going to be a support in the Y-axis and then also a support force in the X-axis because that's going to only allow rotation there. So as you can see, there's no reaction moment between these two. Now, if there's a fixed support, though, that's going to be the case where, this beam is welded or it's placed into concrete. And it's going to be the case where we have Fy, Fx, and then we're going to also have the reaction moment there. And so just to show you guys this too, I ended up finding this video here online. And so this actually shows you the different methods in which, how this correlates to real life. So you can see those. And if you end up bringing up the notes in class, you can kind of zoom in on this a little bit better. But yeah, here we go. So we can zoom in on this right here. So if we have a pinned support, remember that's going to be where rotation is allowed. We're actually not going to have any reaction moment. And so how that correlates into real life is something like this. If we have a roller support, that's going to be the case where we allow rotation. There's also going to be that horizontal movement allowed. And so there's actually like a little slot that these bolts here can actually move through horizontally. Now, if it's a fixed support, however, this is that case where I was talking about how we're going to end up having this where we'll actually weld this together so that it ends up being fixed on there. All right. So in terms of the beam types, different beam types, there's simple beams. This is going to be pretty much 90% of what we're dealing with. Continuous beams, though, also is a possibility. There's also cantilever beams where it's fixed at one end. There's also the case where it's fixed just completely on both ends, right? And so there's going to be moments at each of the ends. There's also propped where it's fixed at one end and then supported at the other. And then there's also beam types where there's an overhang. And so as you can see here, we have a support here, and then there's this overhang. Just as I was saying, 90% of the problems you're going to end up encountering are going to be simple beams. However, whenever we do hop into MD solids and go through the 6 rules, you're going to end up seeing beam types that look like these other variations. So in terms of simple beams, as we're saying, that's going to be our primary focus. What we want to end up doing is there's a process that we want to follow, right? And so we're going to start off by having a beam diagram. And so in the beam diagram, we can see the different types of supports that we have. We can see the different types of applied loads that we have. And what we want to end up doing, the first step is we want to turn that into a free body diagram. Now, just like you guys had learned about in physics, free body diagram is showing just the actual body or the part that is being acted upon by forces. And then it's just showing all of the reaction forces as well as applied forces on that. So we end up getting rid of these supports here. And instead of those supports, we actually have the forces that come from those supports. So just as we were saying, a pin support, that's this little triangle guy, that's going to have a Y support force and then also an X component support force. In terms of a roller, it's just going to have a Y component. In terms of our applied load, that is only applied in the Y axis as well. And so that's why they make this note here for this X support force here. There's no applied horizontal load, so we could actually end up ignoring this guy because this force is going to be equal to 0. Now, how we end up solving these, what we just actually did to be able to tell that this force here is going to be equal to 0 is we ended up using the fundamental principles of equilibrium. Now, at some point in your education so far, you've encountered these. So this is going to be a nice little review, but then we're also going to be applying this to beams, of course. And so what this is stating that the sum of all the forces in the y-axis is equal to 0. So for instance, in here, all of our forces that are acting in the y-axis is going to be this applied load, right? And then we've got these two supports that are also acting in the y-axis. This guy right here is only in the x-axis. And so that's the sum of the forces in the x-axis is equal to 0. So you basically add up all the forces that are in the x-axis, right? And so because it's just this guy right here, that's going to be equal to 0. And then we also have the sum of the moment. Now, as we were talking about, there's this little subscript here, P, that is going to represent any point along the beam that you choose to calculate the moment about. And we're going to have all of these being equal to 0 because our beam is in static equilibrium, meaning if it's already at rest, it's going to stay at rest. It's not going to actually accelerate. So, nice little review of moment in case you ended up forgetting about moment. So a moment is created when a force tends to rotate an object. The magnitude of the moment is equal to the force times the perpendicular distance to the force, so the moment arm. And so how we officially write out this equation is by using this vector notation here. And so just as we were talking about, a vector is anything that has a magnitude as well as direction. And so we have these little arrows up on the top here. Now, what this actually is, whenever you become an engineer, you go to school to become an engineer, you'll end up using this formal equation here, which is where you're going to end up having a vector of the moment And that's going to be equal to the force as a vector multiplied by that distance as a vector. And so what we can end up doing with this is we can basically just take this and say, okay, well, the moment is equal to the force multiplied by the distance that is perpendicular from that force. Or you can say the moment arm times the force that is perpendicular to that distance. And if you multiply those two out, you'll end up finding the moment. So in this case, for instance, the moment that is created is going to be equal to whatever this force is here that's acting primarily in the y-axis multiplied by this distance here, d, which is known as the moment arm. Now, to give you a real-life example, you could think of this as like a door, right? If you end up pushing open a door, if this is the hinge right here, right? Imagine this is the hinge. If you end up applying a force that's out here, it's going to open that door pretty easily, right? If you end up instead applying your force right here, very close to that hinge, what you're going to end up finding is that it's very, very difficult, very hard to actually get that door to rotate open. So that's a real life example of moment. What I'm going to do now is I'm going to actually go through an example here with you all. And so we're going to go ahead and calculate this out. So let's get down to business. So here's the example that we're going to go through here. So you can end up seeing we are given this beam. Now we have a pin connection over here as well as a roller connection. And as you can see, we also have some forces that are being applied to it. So we've got this uniformly distributed load. And so that is always going to be represented with the variable W. And so as you can see, that is equal to 650 pounds per foot. And so what this is saying is per foot that this uniformly distributed load is being applied, it's going to be 650 pounds. And so if you end up taking 20, which is the total distance that's applied, and multiply that by that 650, we'll end up finding out how many pounds of force that uniformly distributed load is giving us. We also have this force P, which is going to be equal to 4,000. And then we have the pound symbol here, which is what they'll use at times to represent something that's in pounds. And so that's why that's 4,000 pounds. So we can see also this is placed 6 feet away from point A or also 14 feet away from point B. All right. So after we have created that beam diagram, our second step, what we want to end up doing is creating our free body diagram. And so now the free body diagram is going to be where we take these supports and we replace those with the reaction forces that those supports will actually give us. And so as you'll remember, the pin support is going to give us a Y force reaction. So we'll put FYA here. And then we're going to also have an X support reaction force as well. And so we're going to go ahead and place that this way. So this is FXA. So what I'm going to do there. Additionally, we have this roller support over here. Now, in terms of that roller support, you'll recall that those just have Y support reactions. And so for that reason, I'm going to put FYB over there. All right. So now this is, after we've got this completed, this is now whenever we'll go to look at the reaction forces and we can start to calculate those out. Now, as we were saying, we have those three equations that we can end up using. Some of the forces in the Y is equal to 0. Some of the forces in the X is equal to 0. And some of the moment at any point along this beam is going to be equal to 0. What we're going to do first is we're going to start off with the most simple thing to do here in this scenario, which is to look at the sum of the forces in the X-axis. Now, whenever I look up here, I will notice that there's only one force that's acting in the X-axis, and so that's just FXA. And so what we do in this case here is we want to add up all these forces that are in the X-axis. Well, since it's just this single one, we just write out FXA, because that's the sum of all the forces in the X-axis, and we're going to put that equal to 0. And so what this tells us is that this force right here is actually equal to 0. And so we can end up noting that up there. All right. Now, the next thing that we can do is we can go to the sum of the forces in the Y-axis. Now, those are going to be equal to 0 as well. Now, as you can see up here, I did end up specifying which direction is positive. We always want to end up doing that with our equilibrium equations here. And so for the sum of the forces in the Y-axis, I'm going to make up be positive. And so I'm going to go ahead and write my arrow up, and I'm going to do plus. Now, what we're looking at here are going to be all of these forces acting in the y-axis. And so as we can see, there's FYA, there's FYB. So we can also see there's P, which is a negative force. And then we're also going to need to take into consideration W here. So we're going to end up talking about that because that's probably the main thing that you're thrown off about. So in terms of the sum of the forces in the y-axis, let's go ahead and begin. We had FYA, which is positive, as we were saying. Plus, we also have FYB, which also is positive. And then we have P, which is a negative 4,000. And I'm going to go ahead and make sure that we write out those units, pounds, LB. Now, we're going to also subtract this uniformly distributed load. Now, just as I was saying, whenever we had introduced this uniformly distributed load here, I was talking about how for each foot that is applied, it's going to be giving us 650 pounds. And so what we can do is if we take that negative 650 pounds per foot, and if I multiply that by the distance that it's applied, which is 20 feet, what you'll end up noticing here is that these units of feet cancel and we're left with pounds. And so this is going to tell us the force that this is going to end up generating in that negative y direction. And so now what we could do is just a double check here. So we've got this y, we got this y, we got this y as well. And so now we can set all these equal to 0. Now what we notice here is that we have two unknowns and we only have one equation in here. And so what I'm going to tell you right now is if you have two unknowns and only one equation, you're not going to be able to solve for both of those unknowns. And so after we solve for this, we're going to need a third equation here to actually use. But let's go ahead and let's simplify this. We've got the good old TI-84 over here. We're going to fire this guy up and we're going to go negative 4,000. So 4,000, I'm going to make sure that that is negative here. Let me do that second insert that I'm going to put in the negative there. Negative 4,000. And then minus 650 times 20, right? Now, what this tells us is that positive Fy plus positive Fyb is going to be equal to, right? If we end up adding these over to the other side, we can end up changing this sign that we've got on our calculator to be 17,000. And that's 17,000 pounds. And so this right here is the first equation. We're going to basically need to end up creating a system of equations, if you remember that from algebra. And so we need that third equation here so that then we can end up solving for these two guys. So we need another equation so that we can end up finding out what FYA is equal to or FYB and then plug it back into this. So just as we were talking about our equilibrium equations, we have the sum of the forces in the x-axis equals 0, sum of the forces in the y-axis is equal to 0. But then I also end up having the sum of the moment. So sum of the moment about any point is equal to 0. Now, this is where there are wise decisions and where you can end up choosing this moment to calculate or the point to calculate the moment about. And so usually what we end up doing is we choose the point that has the most unknown forces acting at it. Now, in this case, we did know that Fxa is equal to 0. We don't know what Fya is, though. So we have one unknown force here at this point A. We also have one unknown force at point B. So it's really up to us on how we want to end up doing this. What I'm going to end up choosing is I'm going to actually calculate this moment about point B here. All right. So we can go ahead and we can get ready to begin with this. So just as we were saying, a moment is a force times a distance. Now, the distance that we're going to be talking about is the distance from point B to that particular force. All right. So what we've got here is this force here of 4,000 pounds, and that is 14 feet away from point B. What we additionally want to end up doing is we want to take into consideration the right-hand rule. What the right-hand rule states is if you end up mimicking the rotation with your fingers, right, and you go in this direction, whatever way that your thumb is pointing, so if it's pointing up, that means it's going to be a positive moment. If it's pointing down, it's going to be a negative moment. And so we can end up going through with this. We can put down anything that is counterclockwise is going to be positive. That is the most common convention here. The other thing you can imagine is if you look at your pen, imagine it being at this point here, B. And if we would end up applying that force, P, if you end up looking at how your pen would rotate, if it is applied that force, that rotation, that way that it's rotating, can also tell you. So as you can see here, this is moving counterclockwise, and so that's why that is going to be a positive moment there. So what we're going to go ahead and do is write down plus 4,000 pounds, and then we're going to multiply that by that 14 feet. And so the unit of moment is pounds times feet. Or if you're talking SI units, it's newtons times meter. Now, what we also have is going to be FYA, which is going to be a negative force. And so if I end up putting my pin here again, have it be hinged on point B, if I end up applying that force here, you'll end up seeing that the pin starts to rotate clockwise, right? Just like in the way of a clock. And so that's why we've got the negative moment here for this guy. And so that's going to be equal to FYA, and that's going to be multiplied by 20 feet. All right. Now, in terms of our forces, well, we took care of this guy. We also took care of FYA. There's also going to be that equivalent force from the uniform load. Now, how we end up determining that, as you can see here, this guy is flat. It's a flat line, right? And so what we end up doing is we have to make an approximation for this. And what we do is we approximate, if it's a flat line here for this uniformly distributed load, we actually approximate it to be halfway between the distance that it is applied for. And so since it's applied for 20 feet, we're going to place that in the center of the beam, which is going to actually be 10 feet in. And so that's that equivalent force from this uniform load. And so remember, that is an approximation. And so what I'm going to do here is we're going to imagine at point B, and then let's say that we have that force that's acting right here, 10 feet in. If I end up pushing with a force, we can see how our pin is rotating. And so it is rotating this way, which is positive, right? Because that is counterclockwise. So I'm going to go ahead and put a positive. Now, what we're going to end up writing down in here is we need to find that equivalent force from this guy, right? So as we were saying, it's 650 pounds per foot. So what I can do is I can multiply that by the total distance that it's applied, right? Which is the 20 feet. So if I multiply that by the 20 feet, we're going to end up seeing that cancels. We're left with the unit of pounds. And so that's the total force that's generated from that uniformly distributed load. And so now, since we have the force there, we can multiply that by the distance that is from our actual point of rotation, right? Our moment, our point that we're calculating the moment about. And so that is going to be 10 feet away. And so remember, this is all going to be equal to 0. So I kind of ran out of a little bit of room there. Probably should have moved it over to the left a little bit. But that's all going to be equal to 0. And so now, as you can see, whenever we look at this equation, we actually have it where FYA is the only unknown in here. And so now what I can end up doing is I can solve for FYA. Then what we can do is, since we had these two unknowns in this equation, I can now plug back in FYA, whatever I find that out to be, and then we'll be able to solve for FYB. So that's how we're using the system of equations here. So what I'm going to do is I'm just going to simplify these numbers, and then I'm going to try to get FYA by itself. So first off, we could do 4,000 times, and I'm going to multiply that by 14. So that's going to be 56,000 pounds times feet. Then we're going to subtract FYA times 20 feet. And then we're going to add on here, we got 650 times 20. That's what that is there. And then now we can multiply that by 10. So we're going to end up with 130,000 pounds times feet. Now that's all going to be equal to 0. What I can now do is simplify this further. I can add these two numbers, and then I'm also going to add FYA times 20 over to the right side of our equation. So we've got FYA times 20 feet. Then remember, we can add these guys up. So we're going to take that 130,000. We're going to add on that 56,000. And so what we're going to end up with there is going to be the 186,000 pounds times feet is our unit there. Now, if I divide this by 20 feet, units of feet are going to cancel. The 20 is going to cancel with the 20 there. We could divide this by 20 feet. We're going to cancel those units of feet. We're going to be left with a unit of pound, which is correct for FYA. It should be the case where that is in just pounds. And so now if we take that 186,000 divided by 20, we can find out that FYA is going to be 9,300 pounds. So that's what that guy is equal to. Now, whenever we go back to this equation, we can now plug this guy in to equation 1 here. And so now what we'll end up doing is we have 9,300 pounds plus FYB is going to be equal to 17,000 pounds. And so now I can subtract that 9,300 pounds from both sides, right? So that we can solve for FYB. Now, FYB is going to be equal to 17,000 minus 9,300. And so what we end up with for FYB is 7,700 pounds. So we can go ahead and we can inbox both of those answers. And so now what we want to do is we want to rationalize our answers and make sure that they actually make sense, right? Because if they don't make sense, then we probably made some mistake. So if we go up here, we have this initial force body diagram, free body diagram, and we have FYB over here. We have FYA. Now what I'm noticing is we have this uniformly distributed load, right? That's placed throughout the entire beam. And then I also have this force over here. What I'm thinking, when I'm rationalizing here, is that because this additional force is closer to FYA, should be the case that FYA is going to actually be a greater support value than FYB, right? This is kind of like if two of your friends or you and one of your friends are carrying a couch. Let's say that this is a couch instead. There is going to be the actual weight of the couch, right? But then also, let's say that one of your other friends sits on the couch while you're holding it, right? As you can imagine, the closer that person gets to you, the more of a force you're going to have to apply, right? And the closer that friend gets to your other friend on the couch, they're going to have to end up carrying greater force. And so because of this, FYA is greater than FYB. And so our answer does make sense. All right. And so that is how we can end up using the static equilibrium equation. Some of the force X is equal to 0, some of the force Y is equal to 0, and some of the moment about any point is equal to 0 to actually be able to determine our support reaction forces. Anyways, hope this video was helpful. Happy calculating. Catch you all in the next video.